Hello and welcome. It's one thing to write code that works, but have you ever stopped and wondered, could this be faster? Today, we're going to jump past just making our code correct and start figuring out how efficient it is. So let's dive into the really fascinating world of time complexity.
So to get our brains warmed up, just take a look at these two loops. On the surface, they look almost the same, right? But which one do you think is actually faster? Or does it depend on something else? This is exactly the kind of question we're going to learn how to answer with total confidence.
And right here, this is the key difference. The loop on the left is totally constant. It doesn't matter what you do, it is always going to run 100 times. Simple. But the loop on the right, its runtime is tied to the size of the input. We use the letter n to represent that input size. So if n is 10, it runs 10 times. If n is a million, well, you get the idea. It runs a million times. Figuring out how our code's performance changes as n gets bigger is the single most important idea we're going to talk about today.
Okay, so this brings us to our first major category, linear loops. Now, in the world of performance analysis, we use a special kind of shorthand to talk about this stuff. It's called big O notation. We'd call this particular case O of n, which you'd say out loud as big O of n. Just think of it like a rating system for our code's efficiency. And in this case, it means the amount of work grows in a perfect straight line right alongside the size of our input.
So just picture a classic for loop that has to go through, say, n different items. As you can see, when the input size n gets bigger, the amount of work our code has to do goes up in a perfectly straight line. You double the input, you're going to double the work. It's a really clean one-to-one relationship.
This table here lets us trace the loop's journey step by step to see how that work adds up. In the first iteration, we do one operation. By the second, we've done two total. And by the time we get all the way to the end, at iteration n-1, we've done exactly n total operations. It's clean, it's predictable, and it's perfectly linear. But what about variations like these? On the left, we're counting down from n, and on the right, we're counting up, but we're skipping every other number. Does this change things? Well, the first one still runs n times. The second one runs n divided by 2 times. But does that really change the fundamental way it grows? And this just nails the point perfectly for that decrementing loop. Right, it doesn't matter if you're walking up a flight of stairs or down it. If there are 10 stairs, you're taking 10 steps. The total amount of work is exactly the same.
And this is the most important rule to remember about Big O. It focuses on the rate of growth, especially when n gets massive. We're not really worried about the exact step count. We care about the overall trend. So whether a loop takes n steps or half of n steps or even a 20th of n, the relationship is still linear. If you double the input, you still basically double the work. That's why we just drop the constant factors and we say all of these are simply O of n.
All right, now that we've got a good handle on linear time, let's see what happens when we take that idea and put one loop inside of another. This is where we step into the world of what's called quadratic complexity, or O(n squared).
Take a look at this simple nested loop. The outer loop runs n times. But for every single one of those n times, that inner loop also runs n times. You see, this isn't addition anymore. This is multiplication. We're doing n times n operations. And this is where performance differences become absolutely huge. An O of n algorithm handling a million things is fast, but an O of n squared algorithm, that could take minutes or even hours. It can totally cripple an application.
Okay, but what about this one? It's a nested loop for sure, but look closely at the condition for the inner loop, j less than I. This means the number of times that inner loop runs actually depends on where the outer loop is in its cycle. This seems different, doesn't it? So is it still O of n squared? Let's find out.
If we trace this one out, we can see a new pattern start to emerge. When the outer loop I is 0, the inner loop doesn't run at all. When I is 1, it runs once. When I is 2, it runs twice. You can almost see it. It's forming a triangle shape, not a square like that last one.
So the total amount of work our code is doing here is the sum of the operations from each step of that triangle. 0 plus 1 plus 2, all the way up to n minus 1. Now, trying to add all that up by hand for a really large n would be, well, a huge pain. So is there a shortcut?
Of course there is. Thankfully, some very smart mathematicians gave us a formula for this exact situation. The sum of a series of numbers from 1 to n is equal to n times n plus 1 all divided by 2. This gives us the exact number of operations without all the manual adding. Okay, so if we expand that formula, we get n squared plus n divided by 2. And now we just have to apply our big O rule again. We only care about the part of the equation that grows the fastest, the term that dominates everything else as n gets huge. And n squared grows way, way faster than a regular n. So we drop the less important n, we drop the constant 2, and what are we left with? Just O(n) squared. So even though it's only doing about half the work of a full nested loop, its growth rate is in the exact same category of complexity. All right, now for a real puzzle. This next loop doesn't really fit the patterns we've seen so far. It's a bit of a brain teaser, and we have to think about it in a totally different way to figure it out. Get ready for O of the square root of n.
Look really closely at the stop condition. The loop keeps going as long as p is less than or equal to n. But wait a minute, p is in our counter. P is being increased by the value of our counter, I, on every single pass. This is a very different kind of growth we're dealing with.
Okay, this looks a little intense, but I promise we can solve it step by step. Let's just follow the logic here. First, step 1, we start with what we know. The loop is going to stop when the variable p finally gets bigger than n. Simple enough. Now, step 2, let's think about p. If we say the loop runs k times, what will p be equal to at the end? It's going to be the sum of our counter I from each pass, 1 plus 2 plus 3, all the way up to k. For step 3, hey, we've seen this series before. We know the formula to get that sum is roughly k squared divided by 2. This brings us to step 4, where we can build a little equation. We can now say the loop stops when our formula for p, which is k squared over 2, is finally greater than n. And finally, step 5 is just a little bit of algebra. If we rearrange that equation to solve for k, which is the number of times the loop runs, we find that k is proportional to the square root of n. And there it is. That's our answer. The time complexity is O of the square root of n. Now, from a performance perspective, this is fantastic. It means that even if you were to quadruple the input size n, you would only double the amount of work. The growth is incredibly slow compared to a normal linear loop.
Whew, we have covered a lot of ground. So let's wrap this all up with a quick cheat sheet to help you remember these key patterns when you see them out in the real world.
Okay, let's do a quick recap of the patterns you can look for. If you see a single loop that goes up to n, or even two separate loops, one right after the other, your first thought should be O of n. If you see loops nested inside each other, whether it's that simple grid or the dependent triangle pattern, you're almost certainly looking at O of n squared. And for that really tricky case where the variable controlling the loop is growing quadratically, the complexity is that super efficient O of the square root of n.
And that's our look at some of the most fundamental loop complexities. But it does leave us with one last, really interesting question. All of our loops so far have involved adding to a counter. But what happens if, on each step, we multiply our counter? Or what if we divide the problem in half over and over? Well, that opens up a whole new world of efficiency, and that is a topic for another day. Thanks for joining me.